In the previous lecture, we used limit laws to evaluate limits. However, in many cases, we are unable to apply the limit laws directly. The most typical examples are rational functions, with 0 being the limit of the denominator. Some of these limits can still be evaluated using the limit laws, provided that we first use algebra to rewrite the formula for the function. We will start the lesson with an outline of the strategy for calculating limits of rational and some irrational functions. Then we discuss an additional tool for evaluating limits, the squeeze theorem. We finish the lecture by applying the squeeze theorem to evaluate the trigonometric limits. We will demonstrate techniques for evaluating limits and the differences between them on the following 3 examples. Notice that in each example, we are evaluating the limit of the same function, x squared minus 4 over x squared minus 5x plus 6. However, in each case, x approaches a different number. X tends to 1 in the first example, x tends to 2 in the second, and x tends to 3 in the third. Let's start with the first example. The limit as x approaches 1 can be computed by application of the limit laws, which in this case boils down to substituting 1 for x. We obtain 1 squared minus 4 divided by 1 squared minus 5 times 1 plus 6 equals -3 halves. So the limit as x approaches 1 of our function is -3 halves. Let's move on to the second example. Since we were successful in using substitution to compute the previous limit, we try it again here. We plug in 2 for x and obtain 2 squared minus 4 over 2 squared minus 5 times 2 plus 6, which gives 0 in the numerator and 0 in the denominator. Since division by 0 is not allowed, we cannot use limit laws to substitute x equals 2. However, x equals 2 is the root of both the numerator and the denominator. We can factor out term x minus 2 from both the numerator and the denominator and cancel. We obtain limit as x approaches 2 of x minus 2 times x plus 2 divided by x minus 2 times x minus 3. Since in the limit we consider the values of x which are close but not equal to 2, the term x minus 2 is never 0. We can divide the numerator and denominator by x minus 2 and obtain limit as x approaches 2 of x plus 2 over x minus 3. We again try the substitution x equals 2, and this time it works. We conclude that the limit equals -4. Now let's turn our attention to the third example. We need to compute the limit of the same function as x approaches 3. We try to plug in x equals 3 and get 3 squared minus 4 divided by 3 squared minus 5 times 3 plus 6, which gives 5 over 0. The division by 0 is not allowed, so we cannot use limit loss to substitute x equals 3. The denominator is 0 at the limiting point 3, same as in the previous example. However, this time the numerator is not 0 at 3. Therefore, we cannot factor out the term x minus 3 from the numerator and cannot cancel it. Limits of the form non-zero constant over 0 are either infinite or do not exist. To determine which answer most accurately describes the behavior of the function near x equals 3, we investigate the one-sided limits. Here we factored out the denominator to get to the answer quicker. When x approaches 3 from the left, the numerator x squared minus 4 tends to 5, and in the denominator x minus 2 approaches 1. Since x tends to 3 from the left, x stays less than 3. So x minus 3 approaches 0 on the negative side. When x is close to 3 on the left, we divide 5 by a small negative number and obtain a large negative number. So the limit here is negative infinity. Similarly, when x approaches 3 from the right, x squared minus 4 tends to 5, and x minus 2 tends to 1. Since now x stays larger than 3, x minus 3 tends to 0, staying positive. Therefore, the limit is positive infinity. We see that the left-hand limit and the right-hand limit are not equal. we conclude that the limit of the function as x approaches 3 does not exist. These examples illustrate 3 typical situations you may run into when computing a limit of a fraction. The first and the easiest case is when the denominator is not 0 at the limiting value of x. Then you evaluate limit by substitution. The second case is when substitution leads to 0 over 0. Proceed by factoring and cancelling common term on top and bottom of your fraction. The last case is when you have an undefined fraction of the form not 0 over 0. This limit is either infinite or does not exist. Based on these cases, we implement the following strategy. To compute the limit of a fraction when x approaches a number, plug in the limiting value of x into the numerator and the denominator. If the denominator is not 0, divide the numerator by the denominator and obtain the answer. If the denominator is 0, but the numerator is not 0, consider one-sided limits to select the best answer from negative infinity, positive infinity, and does not exist. If both the numerator and the denominator are zeros, transform algebraically and cancel common factors in the numerator and the denominator. In the next 5 examples, we will see how we can algebraically transform different functions to compute limits. Let's evaluate limit as x approaches 0, 3 minus x squared minus 9 divided by x. First, try to substitute x equals 0. We get 3 minus 0 squared minus 9 divided by 0, which is 0 over 0. The next step is to transform the formula algebraically and cancel. We square 3 minus x in the numerator and get 9 minus 6x plus x squared minus 9 divided by x. Here 9 and negative 9 nullify each other, which allows us to factor out x in the numerator. Now we can cancel x in the numerator and the denominator. We arrive at the limit as x approaches 0 of negative 6 plus x. The last step is to substitute the limiting value x equals 0 into the transform formula. The limit as x approaches 0 of negative 6 plus x equals negative 6 plus 0 equals negative 6. Our next example is to evaluate the limit as x tends to 1 of x squared plus x minus 2 divided by x squared minus 3x plus 2. First, we try to substitute x equals 1. The numerator 1 squared plus 1 minus 2 equals 0. The denominator 1 squared minus 3 times 1 plus 2 is also 0. In this case, we need to transform the function algebraically and cancel. Okay, the numerator factors as x minus 1 times x plus 2. The denominator factors as x minus 1 times x minus 2. We cancel common factor x minus 1 and obtain x plus 2 over x minus 2. The last step is to substitute 1 for x. Limit as x tends to 1 of x plus 2 over x minus 2 equals 1 plus 2 over 1 minus 2 equals negative 3. The next example illustrates the algebraic technique of multiplying by the conjugate, which we use to treat some functions involving square roots. Let's evaluate the limit as x approaches 4 of square root of x minus 2 divided by x minus 4. We first try to substitute x equals 4. We obtain square root of 4 minus 2 divided by 4 minus 4, which gives zeros in both the numerator and the denominator. The second step is to perform an algebraic transformation, which allows us to cancel the factor x minus 4. We can achieve that by multiplying and dividing the fraction by the conjugate of the numerator. The conjugate of square root of x minus 2 is square root of x plus 2. So we multiply the numerator and the denominator by square root of x plus 2. In the numerator, we obtain the difference of squares. Square root of x squared, which is x, minus 2 squared, which is 4. In the denominator, we have the product of x minus 4 and square root of x plus 2. Now we can cancel the common factor x minus 4 and get the limit as x approaches 4 of 1 divided by square root of x plus 2. Next, we evaluate the last limit by substituting x equals 4. We get 1 divided by square root of 4 plus 2, which is 1/4. Example number 4 illustrates the same technique of multiplying by the conjugate. We need to evaluate the limit as x tends to 5 of x minus 5 divided by square root of x plus 4 minus 3. We try to substitute x equals 5 and get 5 minus 5 over square root of 5 plus 4 minus 3, which is 0 over 0. We proceed to the second step, transform algebraically and cancel. Here the algebraic transformation consists of rationalizing the denominator. The conjugate of square root of x plus 4 minus 3 is square root of x plus 4 plus 3. So we multiply the numerator and the denominator by square root of x plus 4 plus 3. We leave the numerator as a product of x minus 5 and square root of x plus 4 plus 3. In the denominator, we obtain the difference of squares. Of square root of x plus 4 and 3. The denominator simplifies exactly to x minus 5. We cancel the common factor x minus 5. Now we just have to substitute x equals 5 into the limit of square root of x plus 4 plus 3. We obtain square root of 5 plus 4 plus 3 equals 6. Our last example is to evaluate the limit as x approaches 1 of 1 over x minus 1 minus 2 over x squared minus 1. We try to substitute the limiting number 1 into the formula and get 1 over 1 minus 1 minus 2 over 1 squared minus 1, which gives 1 over 0 minus 2 over 0. Since the value of this expression cannot be determined, we transform it algebraically. We can rewrite it by combining the fractions and simplifying. Notice that the denominator of the second fraction, x squared minus 1, factors as x minus 1 times x plus 1. Since x minus 1 is already present in the denominator of the first fraction, we just need to multiply and divide it by x plus 1. Now both fractions have the same denominator. We combine the numerator x plus 1 minus 2 and get x minus 1 divided by x minus 1 times x plus 1. We cancel the common factor x minus 1 and get 1 over x plus 1. Now we can substitute x equals 1. Limit as x approaches 1 of 1 over x plus 1 equals 1 over 1 plus 1 equals 1/2. The algebraic techniques we just discussed are often ineffective for evaluating limits of trigonometric functions, and other tools are required. One such tool is the squeeze theorem, which is sometimes called the sandwich theorem or the pinching theorem. Consider function f of x that is trapped between two functions, g of x and h of x, on some interval around x equals a. This means that the graph of f of x lies between the graphs of g of x and h of x, with g of x as the lower and h of x as the upper functions. Algebraically, we write g of x is less than or equal to f of x, which is less than or equal to h of x for all x near a. The squeeze theorem applies when f of x is not just trapped, but actually squeezed at a point x equals a by functions g of x and h of x. By this we mean that f of x is between g of x and h of x, and g and h have the same limit L at a. We do not require that f of x be defined at x equals a, but it is clear graphically that f of x must approach the limit L. We state this formally in the next theorem. If f of x is greater than or equal to g of x and is less than or equal to h of x when x is near a, except possibly at a, and the limit as x tends to a of g of x equals the limit as x tends to a of h of x equals L, then the limit as x tends to a of f of x exists and also equals L. In the next example, we will show how to use the squeeze theorem. We will evaluate the limit as x tends to 0 of x squared sine 1 over x. First note that the limit at 0 of sine of 1 over x does not exist because of oscillation. We established this fact graphically and numerically in our first lecture on limits. Therefore, we cannot use the product law to calculate this limit. Instead, we apply the squeeze theorem. We know that the sign of any number lies between -1 and 1. Therefore, for all non-zero x, we can write sine 1 over x is greater than or equal to -1 and smaller than or equal to 1. We can multiply any inequality by a positive number. Since x squared is positive for all non-zero x, we multiply each side of this inequality by x squared. We get that x squared sine 1 over x lies between negative x squared and positive x squared. Now we let x go to 0. Since the functions negative x squared and x squared both approach 0 as x tends to 0, the middle function x squared sine 1 over x is forced to also approach 0. By the squeeze theorem, we conclude that the limit as x approaches 0 of x squared sine 1 over x equals 0. To gain a visual insight, we graph all three functions. The function in question, x squared sine 1 over x, is graphed in red. It is trapped between two parabolas. The upside down one, negative x squared, in blue, and x squared in green. The red function oscillates between the blue and the green parabolas, but at 0 it is squeezed and therefore is forced to have 0 as its limit. When we first introduced the notion of a limit, we investigated the behavior of function sine theta over theta near theta equals 0. On the basis of numerical and graphical evidence, we concluded that the limit as theta approaches 0 of sine theta over theta equals 1. Now we can prove it using the squeeze theorem. To do so, we must find functions which squeeze sine theta over theta near theta equals 0. These are provided by the following geometric argument. Consider a unit circle and let theta be an angle in the first quadrant. We compare the area of the three geometric shapes: the area of the red triangle, the area of the blue sector, and the area of the green triangle. It is clear from the picture that the green triangle has the largest area of the three. The red triangle has the smallest area, and the sector is in between. Let's compute these three areas. The red triangle is a right triangle, so its area equals a half of the product of its sides. Since the hypotenuse is 1, the adjacent side equals cosine theta, and the opposite side equals sine theta. Thus the area is 1/2 sine theta cosine theta. The area of a sector of some angle is a half of the product of the angle and the square of the radius. Since our circle has radius 1, the area of the blue sector of angle theta is simply 1/2 theta. The green triangle again has the right angle, so its area is a half of the product of its sides. The side adjacent to theta has length 1, because the radius of the circle is 1. The length of the opposite side is tangent theta. In case you do not remember this fact from trigonometry, it is easily deduced by setting equal the ratios of the corresponding sides of the similar red and green triangle. The area of the green triangle is 1/2 tangent theta. We have therefore shown that 1/2 sine theta cosine theta is smaller than 1/2 theta, which in its turn is smaller than 1/2 tangent theta. We can divide an inequality by any positive number. Since we consider theta only in the first quadrant, sine theta is positive. We divide this inequality by 1/2 sine theta. Now we cancel common factors. On the left-hand side, we cancel 1/2 sine theta. In the middle, we cancel 1/2. On the right, we simplify tangent theta over sine theta to be 1 over cosine theta. We obtain the inequality cosine theta is less than or equal to theta over sine theta, which is less than or equal to 1 over cosine theta. We proved this inequality for positive theta. However, all three functions, cosine theta, sine theta over theta and 1 over cosine theta are even. They do not change when theta is replaced by negative theta. Therefore, this inequality is also true for negative theta in the fourth quadrant. Now we are ready to use the squeeze theorem. When theta approaches 0, both cosine theta and 1 over cosine theta have limit 1. By the squeeze theorem, the limit of theta over sine theta must also be 1. We proved that theta over sine theta approaches 1 at 0, which is a useful fact by itself. To compute the limit of sine theta over theta, we notice that sine theta over theta equals 1 divided by theta over sine theta. Therefore, the limit as theta tends to 0 of sine theta over theta equals the limit of 1 over theta over sine theta. According to our computation, the denominator approaches 1. This gives that limit as theta approaches 0 of sine theta over theta equals 1, as required. We will use both limits of sine theta over theta and theta over sine theta at 0 repeatedly to compute a variety of trigonometric limits. Let's evaluate limit as x tends to 0 of sine 4x over x. We need to rewrite this limit in terms of the limit of sine theta over theta. Since the argument of sine is 4x, it is natural to think of theta being 4x. To obtain the same value theta in the denominator, we divide and multiply the function by 4. We take out the constant multiple 4 from the limit. The limit as x tends to 0 of sine 4x divided by 4x is exactly the limit of sine theta over theta when theta tends to 0, with theta equals 4x. Notice that here we do need to check that theta equals 4x tends to 0 when x tends to 0. Before concluding that the limit is 1. Since we had an additional factor of 4, the value of the original limit is 4 times 1 equals 4. The next example is to evaluate limit as x approaches 0 of tangent x divided by sine of 2x. We check that the substitution x equals 0 leads to the indeterminate form 0 over 0. tangent of 0 is 0, and sine of 2 times 0 is 0. We need to algebraically transform the function to utilize the limit of sine theta over theta. First we write tangent x as sine x over cosine x. Then we multiply the numerator and the denominator by 1 over x. Now we rearrange the terms and get 1 over cosine x times sine x over x in the numerator and sine of 2x over x in the denominator. In the numerator, sine x over x has the desired form. In the denominator, we have sine of 2x over x. As in the previous example, we write it in the form sine theta over theta with theta equals to x. To do that, we divide and multiply this fraction by 2. Now we are ready to let x go to 0. In the numerator, 1 over cosine x approaches 1, since cosine of 0 equals 1. Sine x over x also approaches 1 when x tends to 0. Sine of 2x over 2x is of the form sine theta over theta, where theta equals to x. This means that this limit is also 1. We obtain that the limit of tangent x over sine 2x equals 1/2. The last example is to evaluate limit as x approaches 0 of sine x over x plus tangent x. We check that substitution x equals 0 does not yield any meaningful answer. Indeed, we have 0 over 0. Again, we will use the fact that sine x over x approaches 1 as x tends to 0. To obtain expressions of the form sine x over x, we divide the numerator and denominator by x and get sine x over x divided by x plus tangent x over x. The numerator is in the desired form. In the denominator, we divide term by term x plus tangent x over x and obtain 1 plus tangent x over x. We rewrite tangent x as sine x over cosine x and rearrange the terms. Now we are ready to let x go to 0. The limit of sine x over x is 1, and 1 over cosine x also approaches 1 at 0. since cosine of 0 is 1. The limit equals 1 over 1 plus 1 equals 1/2. This is the end of our lecture.